This is our second meeting, and today we will talk about the following topics as listed here. We will spend a little time talking about quantum computing, as one of the student shown some interest to know about it. Then we will talk about the various pluses and minuses of quantum computing, the errors that bedevils this subject area of quantum computing, talk about the various developments that have taken place on the theoretical side of this, which talks about the error correcting codes. Leaving aside this futuristic topic of quantum computing, we are going to talk about the scientific computing in the classical sense, and that will be beginning with a discussion on requirements of good computing. One of the requirements is listed here as resolving a sharp gradient, and this comes about in resolving various boundary and interior layers, shock waves, hydraulic jumps, sonic boom, propagation of wave fronts, and this will be followed by an example on boundary layer. We will talk about the structure of boundary layer, why we need transformation to resolve this inner layer which is close to the boundary, and the essential goal in this whole approach was to bring about simplification which will allow us to go from a partial differential equation to ordinary differential equation. So, we will spend on that, and we will be finally finishing the discussion with a description of Blasius boundary layer. In quantum computing, you actually use what is called as qubits. Now, qubits are basically quantum states of microscopic system, like electronic state of atom or ion. So, this basically is a microscopic state. Atom or ion, whatever we do. So, it immediately suggests to you that quantum machines would be best suited for problems of that kind. For example, you want to simulate some quantum system, then you should use a quantum machines. Okay. So, maybe the rich areas where it would find its niche activity would be in chemistry, or could be in, say, material science. For example, people have tried to investigate high temperature superconductivity. This is a potential area where it could really work, and of course, people have a lot of hope that you would be able to get some idea. Well, two things I just want to request to all of you, that since we are recording it, so we will request you to please be in time, so that once the class started, it kind of distracts everyone. And do not hesitate to ask any question at any point in time. Otherwise, I will go very fast. If I have some feedback, then I would know where to stop, where to pause, where to emphasize. So, one of our students, Shagato, asked me about quantum computing. So, I collected some information, I am sharing it with you. So, what happens is, in quantum computing, actually you do not depend upon the binary state of binary state of like the qubits do not depend on either 0 or 1. It could be a superposition. So, it could be anywhere in between 0 and 1. Some of you may have known this is what is done in fuzzy logic, right? You can see them all in your camera, washing machines, they are used already, but that is not microscopic property. I mean they are totally a classical operations, fuzzy sets and logics as defined by Zadeh. It's been there for last 40-50 years. So basically in Q machines, quantum machines, you depend upon what we may call as superposition of states. But by definition, quantum mechanics is a very hypersensitive system, right? You measure something and every other thing is affected. So what happens as a consequence? As a consequence, you get what is called as entanglement. So say you are trying to compute something using one qubit, but one qubit cannot work in isolation. It is going to bring in, because of the quantum property, other qubits also into picture, and that is what contributes to what we call as entanglement. Please do understand that these are all theoretical construct. Quantum physicists are thinking of potential pitfalls and they are figuring out where the potential difficulties would be, and they are trying to unravel some of those difficulties. So entanglement is one such difficulty which people are expecting that it would happen when you have a practical computer using quantum principles. Then this dependence or superposition of state would automatically lead to entanglement, and once you have entanglement, means it is an interdependence of qubits. The qubits are dependent on each other. So basically this also has a positive property, because if you sort of identify a particular qubit to do some operation, the other qubits are also taking part in that computing through the quantum property. So it is almost like similar to your parallel processing. The same problem is being addressed by many qubits simultaneously. So that is what happens. So you can say that this has some relation to parallel computing. Okay, so this is sort of a simile, not exactly you will be using parallel computing, but it has the potential of doing that. There is one aspect that really kills the joy, is basically the quantum superposition that we just now talked about. Is not stable. This is a major issue, stability of computing. You try to compute something, you would like the system to behave in a stable fashion for quite some time. But in quantum computer, the problem of stability is a major issue, because the moment a qubit interacts with its surrounding, as I told you, the quantum principle expects that everything would change. So, the system is not in equilibrium, I mean it has changed by itself. This is what is called as decoherence. So, this is a major issue of quantum computing, that the essential property of quantum state, the way they behave, leads to decoherence. Computing would be quite unstable, and as a consequence you will have large error. How large? That is the question. So, for example, if you look at the gating operation in a transistor, you get an error of the kind 1 in 10 to the power 14 operations. That is why you are often advised to reboot your system, right. So, if you continuously keep working, it is quite likely that you would make error in that with that kind of statistics 1 in 10 to the power 14. Whereas quantum computers would give you an error which is 10 million times more. Okay. So, this is also something that is agitating the mind of people working in this area. So, people have started working on what is called as quantum error correcting codes. This lot of work has been done in 1990s, lots of papers have been written, but the bottom line remains the same, that we have to wait probably another decade or more before we start seeing quantum computers. So, I do not know if you have followed recently the news. A couple of things were announced last week. One was by this group from EPFL in Switzerland. They made an announcement in a conference in Oxford that they have been able to simulate human brain. Now, what does simulation of human brain means? So, that was a very interesting newspaper quote, that it is something like 10,000 laptops working together. Well, I did not get much out of it, but the other thing that we probably have seen in the newspaper is some US group has come out with a paper in Journal of Biotechnology or Biological Sciences or something. It's in that work they have talked about bacterial computing. So, they have used E. coli and tried to solve a problem which is called the traveling salesman problem. You have heard of it, right? So, you have cities and a salesman wants to visit all the city. You try to minimize the path taken, minimize the time taken, all kinds of possibilities. Although they wrongly attributed it to a Hamiltonian path problem, it is not. It was actually a traveling salesman's problem, but they also said that they could do with about only 3 cities. So, 3 cities actually you do it on the back of an envelope, right? You do not need to go to a computer, but it is a beginning anyway. So, there are lots of things that is happening in computing, but as far as this course is concerned, we stick to classic computing, right, with very deterministic methodologies, very definitive problems which have been explored for a long time. And so, with that I suppose a brief introduction to what I talked about yesterday should wrap it all up, and let us look at some real serious business. So, start the second module of our course after the introduction. What are the requirements of good classical computing? Well, the first and foremost is that when you look at the system behavior, the property as given by functions usually have sharp gradients. So, we need to resolve those sharp gradients. Here are some examples taken from different branches of engineering or science, what you might recall. The first one is familiar to you who probably have taken courses in fluid mechanics, right. So, you see that if you look at a flow over a body, very close to the body near the boundary, you have a sharp gradient. The flow behaves increases rather sharply near the body, because at the body the velocity is 0, but then it keeps growing very rapidly. So, you get that what you call as a boundary layer. If such a phenomena is happening not near the boundary, but in the interior of the domain, then we call them as interior layers. So, these are classical problems. People have been looking at it for almost 100 years now, little more than that. This thing is an aerospace engineer or people working in ballistics have been worrying about shock waves. Here is a picture of a bullet. The bullet is going from left to right, and you can see a sharp front of discontinuity, what is called as a detached shock wave. So, across the shock wave, the flow properties jump discontinuously. So, that is an example of a sharp gradient, right. Then if you look at hydraulic jump, which is shown here in a lab scale. So, what is happening here? It is a channel and water is flowing from left to right, and there is this hydraulic jump. It is almost like a shock wave. So, across this jump, the flow properties again change discontinuously. This is something probably some of you have noticed, what is called as the sonic booms. If you have seen this high speed aircraft flying overhead, then you would notice, especially if you notice the rattling of the windows, and you would see that there is a distinct pattern of the signal, the motion that comes about, which looks like a N wave. So, if I am following some variable, it would have some kind of a signature like this. So, it will be quiescent, then it will peak up, then again you will have this kind of a thing. Variation, M waves, these are what is called. So, those are the sonic waves, booms. And then in all disciplines of physics and engineering, wherever you see waves, you have the wave fronts propagating, and this wave fronts also represent some kind of a discontinuity. That is the borderline between the signal and no signal. So, let us try to understand what this boundary layer is, where these sharp gradients come from. So, let us fall back upon the old spring mass system, which all of you are familiar with. Unfortunately, if you notice here, K and C has been interchanged here. K is the dashpot here, and C is the spring, just the other way. I have taken it from a book and I am just following it. This is from Schlichting's book on boundary layer. So, I was just following that. So, basically what you are looking at an equation of this kind, that very simple, a second order ordinary differential equation. But there is a twist in the tail here, is that here we are considering the system where m goes to 0. Of course, if m is a regular quantity, then you can, if I just simply take a basic solution as e to the power lambda t, then of course, this will yield a quadratic. This is a constant coefficient ODE, and those two quadratic, that quadratic will yield two characteristic exponent, lambda 1 and lambda 2, given by here. But as you can see, if m goes to 0, you really cannot directly apply this. So, what do you do? What do you do is that you can see that a naive approximation applied on the equation, governing equation here, by switching this term off will not do. Why? Because that changes the order of the system, right? That changes the order of the system. What you notice that that would immediately yield a solution, which I have purposely written with a subscript O to imply, that is, I will explain to you what I mean by that, and that would be okay. So, this is a solution, as you can see, will not satisfy initial condition. Initial condition, as we may have shown in the previous slide, was that at t equal to 0 you have x equal to 0, and let us say the velocity is also 0. So, if I look at this solution, this satisfies neither. So, apart from the fact that the order of the system has come down, so you cannot satisfy two initial conditions. You are hoping to satisfy at least once, that hope is also dashed, because this does not satisfy even that. So, this shows that this kind of a naive approach will not do. So, we may have to do something different. So, because the impropriety of the solution actually is close to t equal to 0, right at the beginning of the system. So, what we could do is we could indulge in some kind of a transformation. So, we telescope this time. So, we take the small time t, we divide it by n, which is itself is a small quantity. So, I am basically stretching the time. So, this t star is basically the stretched time in terms of the basic time given t. And now, if I call this solution as x I or x inner, then what happens is I could transform this equation. So, basically what you are noticing here, so x I is denoted as the solution, and we are using t star as t by m. Then what happens is of course any derivative would be nothing but d by dt star, and that would give you 1 over m. So, what you can see here, then you are going to get that as m times 1 over m square, and x I am calling it as x I, and this will be dt star square, and this will be k by m dxi dt star plus cxi. Okay. So, now you can of course see this 1 over m goes here. So, m comes there, and these two terms are devoid of that m, which may be going to 0. Now, what you have achieved here, now you can probably look at the limit m going to 0, then that last term drops out, and as a consequence you retain the order of the system. The reduced equation is still a second order equation, and then you can solve it. It is quite easy. One of the exponent is 0, the other one is of course minus k. So, you get the inner solution given by a1 e to the power minus k t star, please note this t star, and plus a2. So, basically if I apply the initial condition, that would give me a2 equal to minus a1 for this 0 displacement condition, and then this is the solution that we get. So, basically what we are now seeing, that we have contrived here a method by which we can obtain a solution which should be valid for small time. Okay. So, we have now two sets of solution, right. One which is valid for small time, which we just now wrote, x inner, which is shown by this red line, and the other solution which we called as the x outer is the line 4, right. Now, you can see that there is a region over which this x I is valid, and there is this other region outside where the x O is valid. So, if I for a moment, instead of starting to think, replace this t by some spatial coordinate like space, then we are having two regions, one very close to t equal to 0 or x equal to 0, and one which is little away. So, that is why which is close to the boundary or which is close to t equal to 0, that is why we are calling it as a inner solution, right. So, we have an inner solution. The same way the 4 gives you what is valid in the outer part. So, what we are now going to do, this is a basics of asymptotic theory, and what you do is you split the original problem into two parts. You get the solution for the inner kernel, and then you get it for the outer part, and then you blend it. Okay. Of course, you can get an exact solution, and which we have shown here for couple of m's. As we decrease m, what we find, the solution becomes steeper and steeper, and this width over which the inner solution is valid becomes narrower and narrower, and that is the reason that we call this as a boundary layer. It is a very thin layer adjacent to the boundary. Okay. So, you have seen that there are many such situations where these boundary layers do occur, not necessarily only in fluids, but let us show you how we can exploit this property of the solution in simplifying some problem. So, this is again I am looking at a fluid dynamical problem. What is happening here is you place a flat surface or a flat plate, as we call them, and it is exposed to a uniform flow u infinity. Then what happens is you are going to see the velocity in the streamwise direction to have a very specific structure. So, what we are looking at, we have a plate here, and if I try to plot, so if I fix a coordinate system x and y, then x component of velocity will grow like this. Okay. And the place where it actually reaches almost its outside value is what we are calling as the edge of the boundary layer. Okay. So, what happens is if I join those points for different location, I get this edge of the shear layer. So, this boundary layer is thin and it is got a 0 thickness at the leading edge, but as you go down you will see that it slowly decreases increases. However, this thickness of the boundary layer delta is significantly lower than L, like the property that we discussed from the previous solution. So, basically one of the feature of the solution is that L is much larger than delta, and these are the governing equations that you are familiar with. This is the mass conservation equation or equation of continuity that we call, and this is your one of the momentum equation. So, when we look at this solution, this is what we call as the Navier-Stokes equation. Okay. Navier-Stokes is the holy grail of fluid mechanics. People have been trying to solve this problem for ages. Almost every Nobel laureate dipped their toe and burnt and left the field. All of you probably are not quite familiar, but Heisenberg's PhD thesis was on fluid mechanics. He got so disappointed, he left and founded quantum mechanics. Einstein also had looked at it in the context of Brownian motion, and he actually had some postdoctoral student like Bob Kreishnan looking at the fluid dynamics problem. Everybody's only goal is to get some solutions of Navier-Stokes equation. The problem is, of course, very simple. The nonlinearity that is here in the momentum equation, this nonlinearity does not allow us having a closed form solution. So, that is why these days many of us try to solve the problem using computers. And when we solve Navier-Stokes equation without using any additional assumptions or approximations, we call them direct numerical simulations. Okay. So, that is a huge area of activity, but let us not digress. Let us look at what happens to a simple flow like this. So, we notice that a thin boundary layer is growing near the wall, which has a 0 thickness at the leading edge of the plate. Well, a thinness of the boundary layer implies that this if I have plotted u here, the x component of the velocity, and this is y, and that is how it looks like. What you notice that it is thin. What? Because the x component of velocity is much larger than the y component, right? Any particle, when it moves in, it converts faster in the x dimension than in y. That is what it makes this layer thin. So, one of the consequences of that observation is, of course, u is much larger than v. The same way we have already noticed that L is much larger than delta. Now, if I have such a flow, what we noticed that mass conservation is given by this equation. This for incompressible flow, and what we have just now said, u is very large compared to v, then again you may be tempted to eliminate this term in comparison to this. That would be a mistake. Why? Because what we are looking at, not the velocities, but their gradient, right? And one of the things that you would never do in any physics activity is violate conservation principle. So, you better be careful whenever you make some approximation, don't violate any conservation property. So, here I am warning you that this equation which represents mass conservation, be very careful. What happens is, of course, that this and this two condition are also synonymous to saying the following, that this del del x, any streamwise gradient, is much smaller than the wall normal gradient. And if you do that, then you would see one property, that both of these terms are of the same order, right. So, basically what we are talking about, x is of order 1, all of you familiar with this order business, right, order of magnitude analysis that we are talking about here, and y inside the shear layer is of the order delta. That is what we talked about. So, what happens if I look at this, if these two are of the same order, what I find that v is of the order of whatever may be the scale for u velocity times delta star, delta by L. So, that is why it is order delta, you see the delta appears explicitly there. U is order 1, L is order 1, so v becomes order delta. So, this gives you v as order delta. So, at least we have made use of the phenomenology. We have seen what is a consequence of what we notice in the experiment, that we cannot eliminate one term at the cost of the other. We have to retain it, otherwise we will be violating mass conservation. Let us look at the momentum conservation principle, or the momentum equation, right. So, that if we are looking at steady flow as we are, so this is your nonlinear term which we talked about, the this is the pressure gradient term, and this is what we have in the Navier-Stokes equation, the diffusion term. I have written down here for you one of the momentum equation. Okay. Now, let us go through this order of magnitude analysis. What we get, u is order 1 as we have notified earlier. So, this will be again order 1, or derivative also would be order 1 operation. So, we will be having an order 1 term, right. What about this? V is order delta, that is what we noted here, right. What about this term, del u del y? Del u del y would be a term which is order 1 over delta, because things are happening much more rapidly in y scale, and that is in the denominator, right. So, that is why it would be that. So, what it means that if delta is small, this derivative is very large to compensate for the smallness of v, and the product taken together again becomes order 1 term. So, both terms are of same weightage. So, we cannot dump one at the cost of the other. Now, pressure gradient is the gradient, the pressure force that we are basically we are applying some pressure differential to get the flow on. So, this is some kind of a forcing term, right. This is the driver of the system. So, this better be order 1. So, we do not tamper with it, because this is what is driving the system. So, this is the giver of the energy. So, it drives the motion. Now, when I look at this, what do I get here? Well, I get this quantity. What is this? This is a kinematic viscosity, okay. And when we are looking at this property of fluid, we know that this is a very, very small quantity itself. So, this nu is by itself a quantity which is much smaller than order delta quantity, right. So, what we have here is this is order 1 quantity, right. What about this? Right. You agree with me? All of you have no problems? If you have no problem here, you notice that this term is significantly larger than that term, right. So, what you can say as a consequence of this observation, that this can be sacrificed. Now, if you have noticed analogy between this problem and the spring mass system that I discussed a little while ago, what is the connection? Both the equations had a small quantity multiplying the highest derivative, right. So, that is why in that spring mass system we could not make that naive operation of m going to 0 and dropping the highest derivative term, then we were unable to satisfy the initial conditions. The same thing here, if we look at it, the nu is multiplied with the highest derivative term, the diffusion operator. And so, we cannot just simply wish away. In fact, this takes us to the history of the subject. You know, if you look at the fluid mechanics as a subject, people have all along thought that viscosity is such a small thing. You know that fluid dissipation, as exemplified by this constitutive property nu, is much larger than say other dissipative losses, like in a structure. You know, you construct a civil structure, there also you have dissipative losses if there is some motion of the structure. But those dissipative losses are 3-4 orders of magnitude higher, and in contrast in fluid mechanics what you find that the dissipative losses are much smaller. So, is it a good thing or a bad thing? As far as the problem solving is concerned, it is a very, very bad thing, because you have to take care of all possible modes those would be excited in a system, because they are not damped out. But in most of other situations, you would notice that this dissipative losses, even say electrical system, ohmic losses is massive, and this quantity in fluid dynamics is such a small quantity that it allows you to retain all the modes, and that means trouble, because you have to be talking about very, very large degree of freedom system. Okay. So, as we have said that the smallness of this quantity contributes to the formation of the boundary layer. The property of the solution comes when the highest derivative is multiplied by a small quantity, that is exemplified here. This although this analysis, order of magnitude analysis, tells us that we can drop this term in comparison to the second diffusive term. So, what we get as a consequence that equation what I have just now written down, and I could do the same exercise with the y momentum equation. I do not wish to bother you. You can look at that equation. That would be this. Sorry. You would notice that all these individual terms will be one order lower compared to the x momentum term. See, on the left hand side, these are order 1 term. You will find individually this is order delta, this is order delta, so on and so forth. And as a consequence, what you would find that all these terms are what we call as subdominant. So that's the mathematical term, that all these terms are subdominant, and you end up getting this, that dp dy del p del y is equal to 0. What does it mean? That across the shear layer the pressure does not vary. That is a very good news, because without that I suppose the subject would not have developed, because people were earlier measuring the pressure outside and pretending that was the pressure on the surface, and that pretension turned out to be correct via this analysis, which was only reported in 1904. So, it is not a very old trick. But what happens is that these two momentum equations simplify like this. Taken together, if this derivative is 0, I can make this as an ordinary derivative, and this I have already commented upon, saying that this drives the flow, the pressure gradient drives the flow, and we get such a structure of the flow inside. How do we get it? That is the thing that we are going to discuss shortly. So, what happens? So, we started off with the Navier-Stokes equation, and we get this equation plus that conservation equation that I showed you, del u del x plus del v del y equal to 0. That constitutes what we will call as a boundary layer equation. So, what was the big deal? Well, this big deal was a singular achievement by Ludwig Prandtl in Göttingen in 1904. As I told you, he published this paper and nobody noticed it. For nearly 7-8 years, people thought it was just a simple piece of work, some 7 or 8 pages paper. It was not very important. Then, of course, people realized that this simple trick actually converted the nature of the problem mathematically. If I look at the full Navier-Stokes equation, then what we require to solve it? It has, let us say it is a time independent problem, so we do not have to talk about initial condition. But if I look at the flow inside a domain, it is driven by the boundary conditions, right. That is what we call as a boundary value problem in red. Boundary value problems are those where we are dictated upon by the boundary condition. By dropping this term, actually change the nature of the problem from a boundary value problem to an initial value problem. Initial value problem means, or a marching problem, is something like this, that if I look at this boundary layer growing over this plate, then what we are in a sense saying that equation allows us to get the solution in station 1, then I can get the solution in station 2. See, that is what we are talking about. If I prescribe this thing to you, and if I know whatever has happened previously, some station here, that would allow me to evaluate all these quantities on the left hand side, and solution of this equation will tell me how this u structure is versus y. That is what we plotted. That is what we plotted, that it would look like this. So, that is the solution coming out from this. We will talk about little more, but the essence of the activity is that we have really converted the boundary value problem to a marching problem. So, I will solve this, next I will solve this question. If I have this solution, I can march there, and there goes the story. So, what happens is, we are going to talk about this classification of partial differential equations probably in the next module. So, but you understand that this is a revolution, because think of, you have a domain, you want to solve a problem, you have say problem with, let us say 100 points in the x direction and let us say 100 points in the y direction. So, if I am trying to solve the Navier-Stokes equation, then I would have unknowns which are 10 to the power 4, right. So, if I convert all these differential equations into linear algebraic equation, that is what we do in computing, we will see that. What we would find that we will have to solve a set of linear algebraic equation with the matrix size 10,000 by 10,000, and it is not a very trivial issue. Even if you look back in 1960s, that was considered very formidable. Yesterday I told you about benchmarking on the computers. Now we do it 2 million equations, right. That is considered the low end of the job. But if you now, instead of solving this problem, boundary value problem involving 10 to the power 4 unknowns, if you try to solve the marching problem, then you would be solving a problem with variables of dimension 100. So, this actually you could do it even with a desk calculator. That is what the way it happened. Some of the students of Prandtl, namely Blasius, they were the pioneers in extracting the benefit of conversion of this boundary value problem to a marching problem, and people were able to get the solution of the viscous action for the first time in the history of fluid mechanics, and this ushered in a totally new era. So, that paper in 1904 written by Prandtl changed not only fluid mechanics, mathematics irreversibly. I think you will find millions of mathematicians make a living out of asymptotic theory. They did. So, this insight into the nature of the solution led us from what we call converting an elliptic partial differential equation into a parabolic partial differential equation. We will see that. Well, the genius of Blasius did not stop there. He was a clever fellow. So, what he said, that I will try to even do something better. He said that if I look at the boundary layer developing, then I could find out some combinations of x and y in such a way that the solutions for that fixed value of that combination will determine the solution uniquely there. So, what he did, he said that look, I will find out a combination of x and y, and I will call that an eta, so that the solution will not be dependent on x and y separately, but that could be written down as a function of a single variable eta. Whenever we can do this, we call this as a similarity transformation. So, what we are saying that this point is similar to some other point here, which may be another point here. So, we could probably draw a line across which the solution has the same value that is given by this u of eta, right. So, let us see how it goes. Blasius actually introduced this eta in terms of this combination. So, what is the idea? The idea is the same that what we did with the spring mass system. Wherever we have problem, we stretch the coordinate. The same thing, if a boundary layer is forming very close to the wall for very small thickness of y, you stretch it open, and that stretching is achieved through this. I do not wish to get into this. There is a formal subject called Lie group transformation. That is where you basically come out with all this similarity transformation. This is a very involved subject itself. So, you can see what one 8-page paper can do, that it has given many branches of physics and mathematics over the last 1 century. But once you do that, you can actually get the solution which was earlier a function of x and y. Now, it becomes a function of single variable eta. So, if we can now reformulate, rewrite that equation not in terms of x and y, but in terms of eta, then we would have done a wonderful thing. What would have achieved? We would have converted the PD into a ODE. So, you see, that was the really remarkable insight of Blasius when he talked about it, and then he also introduced what we now call as a stream function. Well, we knew it all along. So, what happens here, we write it like this. So, f is some kind of a non-dimensional function, okay, and the scaling is done with respect to this. Why do we need psi? Well, very simple. I told you, never violate mass conservation, right. So, for this problem, if I introduce the stream function, I am guaranteeing mass conservation. So, this is the ironclad guarantee that you would not fall to the trap of violating mass conservation by the introduction of psi. Well, once you have psi, you could of course get the u component of velocity that is given by this, and v component of velocity which is given by this. Okay. If I do this, then what I am trying to do is get in eta and f in this equation. So, what I would get from here, of course, you can see del eta del y is given by u infinity by mu x, and del eta del x will have okay. So, basically this works out to, so I can use this. So, I will differentiate this with respect to eta, that will give me df d eta times d eta dy, that is this expression, and I have already this quantity sitting up front, and then I have this u infinity by mu x. So, this basically gives me u infinity df d eta, or I could just simply write it as with a prime, conserves space. Okay. So, the same way we can get this expression for v. I think yeah, you can work it out, and you will see that this is going to be half okay. Now, you can keep doing those manipulations, working out the various terms in your boundary layer equation. So, you can plug those quantities and eventually you will get that equation that I have written. You can work it out yourself. There is a factor of 2 there. Is there a 2? Yeah. So you can see that's a sequence of observation that led us from a nonlinear PD to a nonlinear ODE. The good news is, of course, as I told you, that I could perhaps use a mechanical desk calculator to solve it, and people started solving it. These are some observations that we noticed, that similarity solutions are not restricted to only fluid mechanics. You would see in all disciplines. They have been formalized by Lie group, and as I told you that we really stretched that y into eta, and thereby that sharp gradient problem has been resolved by having this simple ODE. So this similarity solution demonstrates a means to really converting PD to ODE. This is another single achievement in pre-computer era. I mean, this was a big deal that we can talk about. So basically then, one of the property we just now talked about, resolving sharp gradient, led us to all this. So we have seen that there are ways and means by which we can simplify the problem and end up with ODE. So what I would do is very quickly give you a review of solving ODEs. I am sure all of you are familiar. Is there anyone who doesn't know how to solve ODEs? Don't bother, even if you don't. We'll follow it as we go along. And one thing about ODEs is that the study is rather simple, because you can take any order ordinary differential equations, you can cast them in a set of first order ordinary differential equations. So if I have a method for solving a set of coupled first order ODE, I am mostly done. I can use that same technique for solving all ODEs. So that makes the job rather simpler. So for example, looked at here at y double prime plus q y prime plus r equal to 0. So set z equal to y prime, then you will get z prime equal to minus q z minus r. So basically it's a 18a or b you would solve instead of 17. That's what is the idea. Now, of course, even when you are solving ordinary differential equation, you need to have what you call as auxiliary conditions. Why do I use a generic term, auxiliary condition? You are familiar with boundary condition and initial conditions, right? So auxiliary conditions are basically a compilation of all. In some problems, you will require both this type, initial and boundary value problems. In some cases, you just require the initial conditions. In some cases, you just require the boundary conditions. For example, this Blasius's equation that we have is a third order ODE. So we need 3 auxiliary conditions. So I think I will just stop here, that we need to really find out what are these conditions, how do we solve it, and we will wrap it up in the beginning of next meeting. Okay? Thank you.